Hello everyone. Today we are going to talk about how to carry out a few experiments in the lab. Polymeric biomaterials are prepared with different morphologies. Some of them are made as beads, some of them are made as films, some of them as nanoparticles, and also as electrospun fibers. So I am going to show you how to make each one of them. For example, if you take beads, they are used quite a lot in bone implants. When there are bone defects, filling of bones, beads are used. You can have beads filled with antibiotics or any antibacterial material. If you are going to make films, films are used as diaphragm patches, heart patches, wound dressing, and so on. If you are looking at electrospun fibers, it's used as scaffolds. It's again used as wound dressing material. If you are looking at nanoparticle, they are used quite a lot in drug delivery systems. So this polymers can be prepared with different morphologies, and they find applications in different areas in the biomaterial field. So we will look at each one of these, how it's prepared using a simple standard polymer system. We will look at how to make beads of calcium sulfate. For example, if you look at this, these are 4 mm calcium sulfate beads, and it's used in bone filling, bone defects after an orthopedic surgery. Calcium sulfate, as you know, is biocompatible, so it also prevents biofilm formation and so on. Okay, we can also incorporate drugs, antibiotics into it, so that the drug gets slowly released and it prevents biofilm formation. So you need around 700 microliter of water for about 1 gram of calcium sulfate. You need to use ultra pure water here. Okay, so I have taken 5 times. That means I have taken 5 grams of calcium sulfate and 3.5 ml of ultra pure water, because look at these molds. Okay, here we can make 4 mm beads, here we can make 5 mm beads. So if you want to cover as much area, then you need to correspondingly take the same ratio. So for 1 gram of calcium sulfate, we need 700 microliter of ultra pure water. Okay, so we need to mix it up well. Okay, so here I have taken 5 grams of calcium sulfate. Okay, I weighed it and I take it in a mixing. There is a magnetic stirrer inside, so I pour them all together inside, and then I take the ultra pure water. This is your pipette. So we mix them here. As you can see, slowly it starts getting mixed. This is called calcium sulfate hemiacetate. So it's got half H2O. It's also called plaster of Paris. You must have all used it long time back. If you have a fracture. Okay, so it easily sets very fast, and if you want, you can add antibiotic, whatever type of antibiotic you want to use, so that it can be used as a drug delivery system also, especially if there are any initial implant related infection that can be completely avoided. So you can see it's getting well mixed. As you can see, the calcium sulfate is completely dissolved. We can stop the mixing. Now we can pour it. So as I said, we can take more quantity depending upon how many beads you want to make. So here I am going to show you a very small region. We just have to pour it on top of this. and then we have this applicator, so we need to tap it a little bit so that the liquid flows nicely inside. So as you can see here, it's filling up the holes, and we need to tap it. Okay, so it's done. Very dilute. Done. So I need to leave for about 15 minutes so that the water evaporates and you get solid material in this. For convenience, we have done it before, so I can show you that. So this is made up of rubber, so it's quite flexible. It's available in the market, so we can just buy it with different diameter sizes. Okay, so once it's completely dried, as you can see here, we have made beads here, so we can take it out here by inverting it. See, you can see this is how the beads will come out. As you can see here, these you get beads of about 4 millimeter in diameter. Okay, and these are beads which are used quite a lot in orthopedic implant surgery, bone filling, bone defects filling, after a surgery, joint filling, with or without antibiotics. Because it's biocompatible, it will not cause any adverse reaction to the human, and we can, as I said, do it with the antibiotic and without. We can even think of making beads of hydroxyapatite and so on. This experiment is going to be a demonstration of making a PVA film. PVA is a polyvinyl alcohol. It's a FDA approved polymer. It finds application in wound dressing because it's got a gelling properties. So it can be made into a hydrogel. It's also used in drug delivery. So this experiment will tell how to make a polyvinyl alcohol film, and we can make this type of morphology with the different polymers. We can use water. In this case, PVA dissolves in water, but we can also use solvents. Whichever polymer dissolves in solvents, then we use, and then we can make films out of it. There we can also incorporate antibiotics. We can even put nanoparticles, silver nanoparticles for example, which has got antibacterial properties. Polyvinyl alcohol is a polymer. This particular polymer has got a molecular weight of 140,000 Dalton. So it's soluble both in hot conditions as well as in cold condition. If the molecular weight goes up and up, you may need to heat it up to actually dissolve it, but this polymer can also go in cold condition. So what we do is we take 5 grams of PVA powder, as you can see here, 5 grams of PVA, okay, and then we need 100 ml of ultra pure water. So what we do is this is again got a magnetic stirrer, as you can see at the bottom, okay, and then we add them together, and then we add 100 ml of water. We have to here do both agitation and heating. Around 60, 70, 80 degrees is enough. Lower the molecular weight, faster will be the solubilization here. As you can see, mixing is taking place. We need to heat it up also here. Yeah. And approximately around 15 minutes, this polymer should completely solubilize in water. As you can see, PVA is completely dissolved in water. Once it's done, we need a watch glass on which into which we are going to pour the solution. The diameter can be bigger or smaller depending upon the size of film you want to have, and of course you need corresponding amount of the PVA solution also. So you need to place it and pour it uniformly inside. So you can pour it inside uniformly so that it spreads, okay. And then we need to leave it like that, so the solution completely covers the entire surface uniformly, and then we need to leave it for 24 hours so that the water completely evaporates and we can get the film which can be peeled out. After 24 hours, the solvent would have evaporated, or in this case water, and we will be able to peel out the film very nicely, as you can see. You can see the PVA film here. It's got a gelling property, that means it will swell when you add water, and it is used in as a wound dressing, and if it is coated with antibiotic, it will also have antibacterial property and so on. So similar approach can be adopted for making films of several other polymers like PLA, PLGA, but you may have to use solvents in those cases also. Okay. This is a nano fiber electrospinning unit. We can make polymers or polymer blends as a fiber form in nano scale. Typically, if you look at a nano fiber mat of a polymer, it will look like this. It is very useful in wound healing applications as well as for scaffold design, and nowadays a lot of interest is shown on electrospinning because they are in nano scale, so there will be more surface area to volume. We can even incorporate drugs, we can even incorporate growth factors so that cells grow very well. So what is the principle of this? We take a polymer solution here, okay, and the solution comes out through the needle. There is a voltage applied at the needle tip. The solution hits the collector where there is another voltage. So because of the positive and negative, the solution travels and hits the collector. As you can see, this is an aluminum foil collector. So we start collecting the fibers, and we adjust the various parameters to get nanoscale fibers in the collector. So there are many parameters you need to control here. The voltage you are applying here, the distance between the needle tip and the collector plate, and the flow rate of the polymer that's coming out. We can adjust the temperature of this chamber. So all these are parameters which one needs to adjust, and of course the polymer solution itself is there. We need to adjust the composition of that solution so that we end up getting a nanoscale fiber, uniform fibers. There is a control software here which controls the electrospin unit. Several parameters can be controlled here. For example, the volume of the liquid polymer solution you have taken is given here, the flow rate at which the polymer solution is coming out of the needle is adjusted here, the diameter of the syringe, the duration, how long you want to run it. So this is a flat plate. In case you have a plate which is rotating, it's called a rotating mantle, we can set the speed of the rotating mantle also here, and also we can tell how long we want to run this electrospinning unit also by setting here. Okay, we have to fill the polymer solution in this syringe, which also has a needle. This is not like a doctor's needle because it is blunt, so that the solution can come out when there is an applied voltage. Here again we are planning to make electrospin fibers of polyvinyl alcohol, that is PVA. Okay, we take 5 grams of polyvinyl alcohol of about 140 kilodalton molecular weight in 100 ml water. If you heat it slightly with about 10 to 15 minutes, it completely dissolves. So I am going to take this polymer solution into this syringe. This syringe is filled with PVA solution. We place it here. After placing the needle in the holder and tightening the screws, this is the positive electrode to which the needle is placed. This is the collector plate on which we have aluminum foil for easy removal. Then we place it in the collector and then tighten the screws. And we clamp it with the negative. Let me explain these controllers here. This is a heater in case you want to heat the chamber to a higher temperature. The temperature inside the chamber is displayed here. This switch is for the lamp here. When we are doing electrospinning, we will switch off this and we will use the halogen lamp, which is shown there, okay, because you can see the fibers coming out only through the halogen lamp. And then this switch is for the controller, and this is for the exhaust, because when you are using solvents you need to remove the solvent vapor, and this one is for the setting up of the high voltage system. Okay, so here it displays the voltage and here it displays the current. We set the voltage and current so that we get very fine nano scale size fibers, and also the fibers are loose so that it does not sort of bind to each other. Now we switch off this lamp and switch on the halogen lamp, shut the door, and we have to initiate the run through the computer so that the polymer solution starts coming out. Then we adjust the voltage and the current. Run பண்ணி stop. Run. We increase the current little bit and then start increasing the voltage. As you can see, the voltage is increasing. Correct?
Increase little, sir. Yes. Now increase.
ஃபார்ம் அது மேலே ஃபார்ம் ஆகிருக்குல்ல. Once we have collected enough fibers, we switch off this machine, we remove the voltage plates, and then we remove the collector slowly, and we can see the deposit of the polymer. We can see the deposit of the polymer nanofibers on this aluminum foil. We can nicely peel it off, as you can see here, from the aluminum foil, and this is a nanofiber of polyvinyl alcohol. If we look under a scanning electron microscope, we should be able to know the diameter of the fiber. It should be in the nano region. So this product can be used for wound healing purposes, burn injuries, and it can also be used as a scaffold material for growing cells of various types. I am going to demonstrate how to make a beta glucan nanoparticle. Glucan is also known as Kurlan, this beta glucan, and it is produced by bacteria. You will also find it in some of the food products also. Glucan is approved by FDA to be used as a gelling agent, and it also has immunomodulatory properties. So it is well approved, and when we make nanoparticles with the beta glucan, we can have drugs encapsulated, sometimes we can have flavoring agents, colorants, and so on. So when we make these nanoparticles, they will be in the order of less than 100 nanometers. We have to add polyvinyl alcohol to stabilize these nanoparticles, otherwise these nanoparticles may agglomerate together and it may form a bigger particle size. Okay, so I am going to show how to make this beta glucan nanoparticle. This is not water soluble, it is soluble in alkali, it is also soluble in acids like formic acid. So we are going to dissolve this in formic acid. So I have taken 40 milligrams of Kurlan or beta glucan. I have taken 2 ml of formic acid, and we are going to mix them at room temperature using a magnetic stirrer. As you can see, this is the magnetic stirrer. I put it inside, and then I stir it. So we stir it for about 5 to 10 minutes so that it completely dissolves into it. As I said, beta glucan is not soluble in water, so it is only soluble in alkali or even mild formic acid. So we do this for about 5 minutes. We need to make a PVA solution. PVA is polyvinyl alcohol. I am using 140 kilodalton. PVA will try to stabilize this beta glucan nanoparticles. So PVA, I have it here. As you can see, it is a fine powder, and then 0.5 grams of PVA I take. And I take 50 ml of water. I again stir it, but here I have to heat it to 50 degrees centigrade, and again stir it here, and I have to heat it to 50 degrees centigrade. Okay, so for another 5 to 10 minutes. So I set the temperature. Yeah. Because PVA is not soluble in cold water, so we are heating it to 50 degrees centigrade. Now I transfer this PVA solution. Now I need to add the beta glucan formic acid dropwise using a syringe into this. Okay, so I have previously prepared beta glucan in formic acid. Okay, as you can see here, beta glucan in formic acid. So now I will take it in a syringe. As I said, PVA will try to stabilize the nanoparticle. As you can see here, small white, that is the nanoparticle of beta glucan. Can you see this? We need to use the probe sonicator to arrive at nanoparticles of beta glucan, okay, stabilized by polyvinyl alcohol. This is the probe sonicator, and we have to keep our sample inside. The sonication will be done for 5 minutes. The sonication will be on for 9 seconds and 1 second off. Because a lot of heat is produced, we have to keep the whole sample inside the ice bath. As you can see here, this is the control unit for the probe sonicator. So we need to set this control. We are going to sonicate for 5 minutes. It will not be continuous, there will be pulses and then stop, but every 9 seconds there will be pulse and 1 second there will be off. We will switch on the control unit of the probe sonicator. We will set the sonication time for 5 minutes. We have set the time for 5 minutes. Now we will set the pulse. Pulse on for 9 seconds. Pulse off for 1 second. Enter. So it's got pulse on for 9 seconds, pulse off for 1 second. It's going to be done at cold temperature. Once the sonicator tip is well dipped, we start the control unit, and the sonication proceeds so that you get nanoparticles. For 5 minutes we sonicate the sample. Once the sonication is done, we have to centrifuge, so we transfer the material into a falcon tube to collect the nanoparticles. This goes into a centrifuge, and centrifugation is done for 10 minutes at 10,000 rpm, and later on to a lyophilizer where moisture is removed and we get very fine product at minus 60 degrees centigrade overnight. The nanoparticle which we prepared using sonication needs to be recovered from the liquid. We use a centrifuge here. We have to centrifuge at 10,000 rpm for about 10 minutes. Use an adapter and place the falcon tube, and we also have to balance it with another empty tube, and then we can close the centrifuge. This is a lyophilizer where the wet nanoparticles can be completely dried by removing the moisture at about minus 80 degrees centigrade, and this is run overnight so that all the water gets removed. After centrifugation and lyophilization, we get a dried nanoparticle of beta glucan or curdlan stabilized by polyvinyl alcohol. As you can see here, this is our product. If we incorporate drugs, then it will be a drug loaded beta glucan. We can incorporate food and flavoring, even coloring agent, so it goes in, it can go into food industries as well. And as I said originally, beta glucan has immunomodulatory properties, it's got anti-inflammatory properties, and it's been approved by FDA. I am going to demonstrate how to prepare isocarrageenan and beta cyclic glucan hydrogel. Hydrogels can be used for wound healing, drug delivery, drug encapsulation. This isocarrageenan is a polysaccharide made up of sulfogalactan, and it's obtained from marine kappa fibers with almost 20,000 molecular weight. And this cyclic beta glucan is produced by bacteria. It's got 10 to 12 glucose in a cyclic form, so the molecular weight will be around 1200 to 1400. Together they will act as a hydrogel. It will be very hydrophilic, it will be able to absorb and retain moisture, and the beta linkage in the glucan also will act as a aid for wound healing, as an immunomodulatory, and so on actually. Okay. So we start preparing this carrageenan beta glucan hydrogel. You will have 75% carrageenan, 25% glucan. This beta cyclic glucan is water soluble, whereas the beta linear glucan or curdlan is not water soluble. This glucan is water soluble, that is why we are using only 25%, and the 75% will be the carrageenan, and later on we will be cross linking with the glutaraldehyde. So initially we start with the 4 ml water. Okay, this is a hot water bath, so we heat this water to 50 degrees centigrade. We take carrageenan, (56.45 milligrams of carrageenan). We add to this hot water. Now we raise the temperature to 70 degrees centigrade for about 15 minutes, so that the carrageenan completely dissolves in it. We can intermittently mix this. This is a mixer. As you can see here, we can mix this. And then again heat it up so that it's completely dissolved. Once that is done, we add cyclic beta glucan, which is 18.75 milligrams to this. Again we heat it up to 70 degrees centigrade, mixing it from time to time. We add 0.75 milliliters of glutaraldehyde. Glutaraldehyde is a cross-linking agent, so it will cross-link the carrageenan and the beta glucan. That is, this is 1%, so we add it to this. You can pour this into a watch glass. And leave it for air drying for 12 hours, that is overnight. This is the overnight dried carrageenan beta glucan film. We need to peel this, so we use 70% methanol water, spray it on top. Now it is easy for you to peel it out. As you can see, this is the glutaraldehyde cross-linked iota carrageenan cyclic beta glucan, the ratio of 75 to 25. We call this hydrogel because it will swell when we add water to this. When we add water to it, it should retain water and swell. That is why it is called a hydrogel. As you can see, the gel has swollen, taking up a lot of water, and this property helps in designing wound healing patches with this carrageenan and beta glucan.